So that's fine. So it's okay. If we have learned about solvent extraction before, but it's okay. We can have some revision, especially for those who have not taken this type of chemistry. So this is very important because it involves, this is one way of preparing your sample, okay? Because there's a lot of extraction needs to be done before you can do analytical or any analysis. So this is one of sample preparation technique apart from what we have learned before. So we have in a form of liquid, which is solvent extraction. And we also have using solvent, which is solid phase extraction. Okay. So let me start. I think we have around 17. So probably there are two more. So for the first part, which is solvent extraction, as I mentioned, many of you probably have taken this. So this is a revision. We are going to learn some theoretical aspects. Uh, application, especially on the sample preparation. It's not moving. Okay. All right. Of course, the formulas are useful, but for the purpose of examination, which is the final exam, there'll be no calculation. Yeah, but it is important for you to know about the formula. Okay, for extraction. Okay, I hope that you know this. This is well, you can use this. You can use HPLC to do some analysis, but this is your actual sample. So how do you prepare from your actual sample into something that a prepared sample or suitable sample for you to do analysis? In this case, you are to do GC, for example. So you are to do HPLC. So how do you prepare from this kind of real sample, actual sample that you obtain into this that you can inject into the machines, or you can put inside some cuvette to do analysis. So for extraction, is more on sample preparation. For example, pre-concentration. What does it mean by pre-concentration? Is to increase the concentration of the analytes that you wish to measure. For example, let's say, I'm not sure whether this is coffee, probably, okay, just pretend that this is coffee beans, okay? And you to analyze the amount of caffeine in these coffee beans, okay? Probably you have samples of Arabican coffee and a few other types of coffee beans, and you are to analyze the caffeine. So you cannot just straight away dump these coffee beans into the machines, okay? So you have decided to use HPLC to run, to analyze the caffeine in the coffee beans. So you have to do some sample preparation. So you might have to crush them, to sieve them, okay? But the most important part is to get the caffeine out from the coffee bean, okay? How do we get the caffeine out from the coffee bean? And let's say if it is probably the caffeine content is too low and you don't have that many samples, then the usage of extraction is also, apart from sample preparation, the other part is to pre-concentrate because we know that some machines, their capability in doing analysis depends on certain sensitivity. Means that if it is the content is too low, then the machine, whatever machine that you intend to use, might not capable to detect the amount of caffeine in this case. So knowing the capacity of the machines, you have to do some pre-concentration step, right? Pre-concentration step. So these two, this is the purpose of doing extraction. In this case, we start with solvent extraction. One is to prepare the sample, okay, into a suitable form to be analyzed by the machine. The second one is to pre-concentrate, to make the concentration higher for the analyte. Okay, so this is quite common. So I think many of you has used this, what we call as separatory funnel. And this is the main components when we use solvent extraction. We have aqueous and we have the organic solvent. Okay, so usually the sample that we prepare, for example, here is in aqueous form. Okay, usually, yeah. So this is not supposed to be water. It can be aqueous. Aqueous means it can be partly some a bit of alcohol. Okay, so just not necessarily 100% water. It can be aqueous. So all the active component is in water, and we want to transfer to organic solvent. So this is the normal phase solvent extraction. So this is the setup. Okay, so we have to know some theory on how to conduct this. And first and foremost, we need to know how the mechanism. Okay, so liquid extraction, in this case solvent extraction, is based on the transfer of solute. Okay, so if you do not know what is solute, okay, solute is the one, well, it's easier to label it as the analyte of interest, the one that you want to measure, the one that you want to transfer into the organic solvent. Okay, so the transfer of solutes from the aqueous, okay, the sample that you prepare, for example, from the apple, from the coffee bean, is here, and you want to transfer the solutes that you wish to measure, for example, just now, caffeine, into organic solvent. Okay, from one liquid phase into another immiscible. So what does it mean, immiscible? You can see here the solvent is divided into two phases. It does not mix. So it's supposed to be immiscible liquid phase according to differences in solubility. So when we choose what kind of solvent to be used in solvent extraction, this is the most important part, is to make sure the miscibility of those two solvents are correct. Okay, it cannot be mixed. It cannot be easily mixed. If it is mixed, then you cannot separate the solvent. Okay, a common analytical challenge is measuring the level of a dilute analyte. Okay, just now I mentioned about the amount of caffeine in the coffee bean. Okay, or in this case, if you are to measure certain types of toxicant in river water. So measuring the level of dilute analyte. So in this case, let's say toxicant is the analyte, and you can imagine river water. So it must be very diluted. And the river water is a complex sample matrix. When you scoop the river water, you're gonna have other things as well. Okay, same goes to body liquid. Okay, so how do you play with that? Okay, so this is the purpose of having separation technique. So in this case, particularly, we are talking about extraction. So extraction of analyte A, meaning that the one of our interest from the river water, for example, from the blood serum, okay, into the organic solvent. Can both, okay. This also, you can see that apart from pre-concentration, okay, it can pre-concentrate pre-concentrate, all right. It also can reduce interferences, okay. So you can imagine that the complex, the sample matrix means that the river water or the plasma is with other things as well, okay. So by having this extraction, we can at least remove the interference from the analytes of interest. So this is also another purpose of having extraction. Okay, so please look at these two structures. Okay, just a moment. So there is, if you look at here, you have acid, acetamine, the right one is easier to pronounce, aminophenol and acetaminophen. So the acetaminophen is actually paracetamol. It's actually paracetamol. Okay, so now if you look at the functional groups for paracetamol, you have amide. Okay, amide here. We have benzene ring and we have alcohol. For aminophenol, we have amine, benzene ring, and alcohol. So what is the issue? Okay, for to get the the paracetamol, okay, acetaminophen, okay, there is a possibility of impurities, okay, and present in the formulated drug above the identification threshold. The compound is a common impurity for in paracetamol tablets. So it can be from the synthesis, also from the starting material, or probably during the thermal degradation of this acetaminophen, right? So how do we get rid of this impurity? Okay, so before we look at the detail of the theory, the formulas, okay, most organic compounds, they have certain polarity, at least some polarity, probably some very polar, some less polar, and it's difficult unless you have a very symmetrical structure, then you have a really non-polar. Okay, so when we talk about extraction, okay, you can see that this is what we call as dissociation. Okay, we will talk about this later, but you can see that there is great effect of pH. Yeah? There is a great effect of pH on the extraction of this organic compound. Okay, so when we talk about extraction, not just the solvent, but also the pH of the solvent. So you have to optimize the pH in order to have a good extraction or a good uh, yield after the extraction procedure. Okay, so this is something that should be in your mind before we discuss further on the theoretical part. Okay, think about the chemical structures of acetaminophen and PAP is the aminophenol. What chemical property is different? Okay, just now I have point out the functional group. Suggest an alternate extraction method from liquid-liquid extraction that could be used to separate aminophenol and acetaminophen. Could pH be useful here? Okay, so if you look at the log P, okay, we will learn about what is P. You can see there is a big difference at different pH. So definitely pH plays a big role for the solvent extraction, apart from solvent itself. Okay, so after completing this topic means the liquid extraction, solvent extraction, you at least can explain the basis of solvent extraction. You can also discuss applications of solvent extraction. Able to use formulas. Okay, this one, no needs, but at least you can understand what are the parameters. Yeah, what are the parameters important in identifying how good the extraction is. Okay, so at least you get to know that. It's not, I mean, you can use it, but it will not be in your final exam. Okay. So as I mentioned just now, solvent extraction for sample preparation, for pre-concentration, to remove interference. Yeah? And it is also possible to change, yeah, to what we call as to derive a new measurable form, derivatization. So this usually, if you are to use GC, gas chromatography, in order to use gas chromatography, you need to have the sample to be volatile, right? Because if you don't have enough volatility, then you cannot use gas chromatography. So in order to do that, you need to change the actual analytes from probably not volatile into something volatile. So we can use solvent extraction to change uh, the property of that analyte, change it into some kind of complex that is volatile. So these three are among the usage of solvent extraction. Okay, so these are some of the parameters, yeah, on how we evaluate how good the extraction is. Okay, so if you look at here, this is what we call as distribution coefficient, which is the P just now, because sometimes it's KD, sometimes it's KP, partition coefficient. So just now what is in the table is P referring to partition coefficient. Yeah. Right. So it can be KD or KP. Yeah. So how does KP express in the form of formula? So the amount of the analyte of interest in this case we name as Z here, in the organic phase over the amount of concentrate, the amount, we are talking about amount, yeah? The amount of the analyte of interest in aqueous. So meaning that the amount of the analyte of interest in the organic solvent over the amount of interest, the amount of analyte of interest in the aqueous phase after the extraction is done. So it is called KD or KP. So if the KD or KP is high, meaning that your system, your extraction system is very good. Yeah, because you are able to transfer the analyte of interest from the aqueous phase into organic phase. That's your objective. So if you choose the right one, the right solvent system, and the right pH, you might have a good Kp or Kd. So this is something, so it is stated here. This assumes that we have ideal behavior at low concentration. Why is that? So now let's look at if we have weak acid. Because we know organic compounds, they have certain polarities. Okay, so what does it mean when we have compounds with certain polarities? You can see that, for example, Ha stands for weak acid, for example. Okay, and we know in order for any compound to be in the organic solvent, it has to be neutral. So if you look at here, a weak acid now is in a molecular form, or molecule is in molecule, it's not in ionized form. Okay, it's not in ionized form. So what we have in the whole system of solvent extraction, if we are to isolate, if we are to extract weak acid, okay, into the organic solvent, this is what happened. Because we know that weak acid will partially ionize. So this is acid-base theory that you have learned. The weak acid is not like mineral acid, it's not like strong acid. It will partially ionize. So some form will be in ionized form, which is H plus and the salt. Some will be in the molecule form, which is the neutral form. So this neutral form, some will be, of course, transferred to the organic phase, the solvent, the organic solvent. This is what you want. So the issue is how much you can get the neutral molecule form of weak acid to be transferred into the organic phase. So that's why you have to control the pH. So I hope that you remember the Lee-Chatelier principle. The Lee-Chatelier principle, where you talk about the equilibrium being shifted to the left, being shifted to the right. Okay, this is related to pH. Okay, so just now, if you look at Kd or Kp, we're talking about ideal condition. Everything is either in aqueous 100% or inorganic. Yeah, but the actual situation, we have a combination where in organic form, of course, in organic solvent, we have the neutral form of the molecule, neutral form of the compound. But in aqueous form, we have a mixture. We have the salt, okay, from the ionized weak acid. And we also have some weak acid in a molecule form, but remain in the aqueous. Okay, so this is the more realistic distribution of the analyte of interest. In this case, we use weak acid because we know most of organic compound, they have different polarity, so they will behave like weak acid. Some in neutral form, some in ionized form. Okay, so DC is called distribution ratio, which is the ratio of the concentration of all the species. Okay, because we have considered some ionized form of the solute in each phase. Solute is the this thing. This analyte is called solutes. Yeah, so this is the formula for distribution ratio. And if the DC is high, we know that we have successfully transferred the analyte of interest, in this case, the weak acid, into the organic solvent. Okay. Just a moment, I have to answer this. All right. Now, if we look at the relation between DC and KD, so this is the relation between DC and KD just now, and also KA. Yeah. So I'm not going to discuss on how you derive from here to get the formula here. Okay, it's important for you to understand this is the relation between DC, distribution ratio, and distribution coefficient, and the acidity constant. Yeah, acid dissociation constant. So if we do experiments, okay, the effect of pH on log DC, okay. So you can see that from the formula just now, okay, DC is related to H plus, yeah, H plus here. So that's why if we construct a series of pH affecting the extraction, if we plot the graph log D versus pH, we can see that there is changes towards the DC value upon pH effect. Yeah? So it's very important to study which pH will be the best for the extraction. Okay, it's not just straightforward. You can do without any uh, uh, buffer. You have to use buffer, and you have to find out which buffer range that is suitable for the most optimum extraction. So this is very important in extraction procedures. Okay, this one is more formulas, so I'm not going to like discuss this. There are so many ways to calculate how much concentration, amount of solute transferred. Okay, these are all just different kind of formulas that you can use. Unless you want to use it in exams, then yeah, some of you had done it during your undergraduates. You can calculate using these formulas uh, to to calculate the amount that is extracted, the amount that will be remaining. So this is just mathematical calculation, because the one that you wish to have, the final goal is to have the most optimum extraction, how much you can get to be transferred into the organic phase, right? So usually it's not enough to just use single extraction. It's not enough. So we have to use multiple. This is of course single extraction. You have to use, let's move on to multiple extraction. Okay, so this is an example, okay, for solute with distribution ratio. The solute means that the one that we wish to extract, with a distribution ratio of 25, meaning that the DC is 25. Show by calculation which is more effective, extraction of 10 ml of an aqueous solution with a 10 ml organic solvent, meaning that you have a single extraction procedure, or extraction with two separate, means that you use 5 ml, 5 ml portion of organic solvent instead of just one of 10 ml. Okay, so in this case that you have single extraction and double, you have two extraction procedures. So the proof if is from here. All right, you can see that using multiple extraction, the one that is collected is much more. compared to the single extraction. So this is the formula if you want to calculate using multiple extraction, where X represent the number of extractions. So this one I think is common sense. Okay, but you can calculate using a mathematical equation. Okay, so I'm not going to discuss this. Okay, there are some issues, of course, for for ideal behavior. There are always issues. You have dissolution from one phase into another due to the solvent issues. Okay, the it dissolve. Okay, it goes. Yeah, sometimes it goes back to the aqueous phase from the organic phase. It goes back, so it's not stable. And there is a possibility that you miscalculate, so you have the solute saturation of a phase, and there is a possibility of reaction of that solute with the solvent. So this is things that we have to have consider before we do solvent extraction. We have to do study if there is any cross reaction between the solutes with the solvent that we use. There is any possibility of reversible reaction. So you have to check all those kind of things before we can do the solvent extraction. Okay. So these are some suggestions. To avoid those problems, you work at low concentrations, maintaining factors. Okay, we study the pH first, and you at least have some precautions. Okay, so just now we are talking about organic means that compound, usually we have some polarity organic compounds like caffeine, vitamins, active component in drug. Just now is paracetamol. So what about metal? Okay, what about metal extraction? How do we extract metal from the aqueous form? Okay, so for metal, we have to think about how to convert the metal ions. I'm not talking about metal solid because they are in elemental form. Yeah, we're talking about metal ions. Okay, so there are ions. Yeah, definitely metal ions. They are ions. Okay, so you have to think of the how to convert the metal ions into uh, neutral, neutral complex, so that it can be transferred into organic phase. Yeah. So there are two types of how to convert from here. Let's say yeah, this is aluminium 3 plus, and the of course in ionic form, and you cannot you cannot extract the ionic form naturally into organic because it does not dissolve. Yeah, the concept of like dissolve like plays a big role here. So you have to strategize on how to change the metal ions into neutral complexes. Yeah, neutral compound. Okay, so usually the process is we have to do some pre-treatment towards the metal ion, and it is called, the first one is ion association complexes. So what is ion association complexes? Is usually we react the cation, okay, because metal ions is cation, with bulky anion. So I don't really have example here, but I think this is one of the best example. So we have metal ion is complex by anion. Okay, so it's a complex to form a neutral metal anion. Okay, so you have to find a bulky anion to convert the metal ion into a neutral complex. So once it is a neutral complex, then it can be transferred into the organic solvent, because that's the rules. That's the like dissolve like, because organic cannot dissolve ions. Okay, and this is another possible that you can use. For example, this is aluminium 3 plus. So you have this. This is considered as ligand, I think. So the next step is extraction of metal chelates. So this is the one that we can do. Metal chelates is by reacting the ions, cations, with ligands or chelating agents. In this case, hydroxyquinoline as chelating agents. So they will form complex. They will form complex, and it is neutral complexes, and it can be now transferred into organic solvent. So this is the concepts on how you can do solvent extraction for metal ions. I think during undergraduates, most of us did chelating agent EDTA. So by reacting the metal ion with EDTA at certain pH, which is important, we can form a metal EDTA complex, and this can be extracted into organic compounds. So this is an example of metal ligand or metal chelating agent. So this is the name of the chelating agent, the Mg, and here acetate. Okay, so you can see that the chelating agent usually have this active site, okay, that can form. It is not covalent. Yeah, it is called electrostatic interaction, or it might be what we call this. I forgot. It's not. It's the one with more electron contributing to the less electron. Okay, so it's not the normal covalent. I forgot about the name. Dative covalent, I think. Okay, so in metal extraction as well, pH plays a big role. pH plays a big role. Why? Because if you look at here, if you look at the ligand or the chelating agent, there's a lot of H hydrogen here. So, and there's also oxygen with lone pair. And if you don't, if you use, for example, not high pH, low pH, yeah? Low pH, there is a possibility of protonation, protonation of these oxygens. And you can see if it is protonated, then it cannot react with the copper ion. Okay, so I hope that you can study what is protonation. So the protonation can be controlled by controlling the pH. So it's very important to understand the effect of pH before we react this metal ion with the chelating agent or ligand. Okay, right. So I think if there is no question, if there is any question, please do ask, because we are going to take a break for 1 hour, and then we will continue at 8 for SPE, yeah, solid phase extraction. Any questions? Everybody is still not sure what is happening? Any question, guys?
No, Prof.
No
Oh,
problem.
okay, right. So I think I don't want to mix with a solid phase extraction. You can just read through, but we are going to start discuss at 8 o'clock. Okay, see you at 8. Bye.
Thanks, Prof.
Right. So the second part will be solid phase extraction. We discussed just now is liquid extraction. So what's the biggest difference is, of course, one part of the extraction requires a solid absorbent. Yeah, adsorbent. So you should know by now the difference between absorbent, AB, and adsorbent, ED. Okay, so if it is liquid extraction, um, we know that it uses a lot of solvent usually. Okay, so most of the time we rely on organic solvent. There's a lot of food related um, functional food that we consume, probably some herbs, probably some additional food that you think beneficial. The extraction procedure is using organic solvent, and it is known that hexane it is accepted as safe. It is safe for food extraction, but still, when you do extraction by using liquid, you have to remove the solvent. Okay, so the process of removing the solvent can be um, time consuming as well as it's difficult. It can be difficult to remove the solvent in order to get the main component. We're not talking about doing an analysis. We're talking about if you like need to extract very precious active ingredient from certain leaves, from fruits that you know is beneficial. So we have to do like solvent extraction, and the solvent has to be removed, and then we can get that compound that we wish to have. So that is liquid extraction. So what's the difference between liquid extraction or solvent extraction and solid phase extraction? Okay, so of course the name is there, is solid phase. So solid phase extraction is a sample preparation technique using solid absorbent contained in this, we call it cartridge. Well, the cartridge come in different forms. So this is one example of cartridge that we can use for solid phase extraction. We can use column, glass column, okay, so that is also solid phase extraction, which is known as column chromatography. Okay, so why solid phase is very important? Because it at least give you the possibility, the alternative, rather than using a lot of organic solvent, because we know using organic solvent is not green and it's not good for environment. So this is one type of how it functions for solid phase extraction. So this is called bind and elute strategy. So if you have in the sample a mixture of analytes, okay, this is the one that you wish to do the analysis, or you wish to get from the raw sample. But unfortunately, of course, in the sample, there's a lot of other materials, and then they are considered interferent. So how do you do that? Of course, after some preparation of the samples into soluble form, okay, So you add the samples into the cartridge. So this is where the solid sorbent is, the solid adsorbent is, okay? So it is possible, in this case, it is called, as the sample is slowly passed, okay, the analyte and some of the sample, the analyte and some of the sample matrix compounds may be retained. So you can see here, depends on what kind of solvent system. Still, you have to use solvent to elute. But in this case, you can at least minimize the usage of solvent. We can pass through the solvent through the sorbent. Okay, the sorbent has trapped everything here. The adsorbent has trapped everything here. But when we pass through a certain type of solvent, okay, we can design so that the analytes is retained in the adsorbent, okay, whereas the interferon, the one that we do not want to be in the mixture, we can elute out, we can take it out. So this requires you to know the right property of the solvent, which will elute out the interference, which do not interfere with the analytes. Okay, so after removing the possible interference, then we choose another suitable solvent to elute out the analytes of interest that we want to have. So this is called a bind and elute strategy. So this very useful to remove the interference. And the second one, instead of getting the interference out first, we can trap and then get out elute out the analytes of interest only. So in this case, it is called removal trapping strategy. So we, by using again a suitable solvent, we just extract the analytes of interest. Yeah, so we have to know again the property of the solvent to make sure it is compatible, that it will only selectively bind to the analytes of interest in order to extract or elute out. Okay, so this is the one that we are going to discuss next week. One of the adsorbent called imprinted polymer that can be used for this kind of solid phase extraction. Okay. All right. So SPE is used to simplify complex sample. Okay, to remove the interference. In this way, you can purify, reduce the ion suppression. Okay, this one is if you're using mass spec. And again, concentrate the analytes present at low levels. Okay, which if you have a very low concentration, you can flush it out. So now you can gather this. You can pre-concentrate them rather than from the actual running the analysis from the actual raw sample, raw that you have prepared before. Okay, so this is again the same usage, but then a different style. And you can see that it really helps if you want to just separate a tiny bit. You don't have to use a lot of solvent because the cartridge can be designed to be very small. Yeah. So if you look at the cartridge, you can design it to be very small, so you don't have to use a lot of solvent. And the solvent also can be regenerated, yeah, the adsorbent, right? So the next one is there are quite a number of types for solid phase extraction. So the first one is based on adsorption, yeah. The one that I discussed just now is based on adsorption, whether it is trap or bind and elute. Okay. It can also based on ion exchange. So I think if you have done column chromatography before during your undergraduate, so it is considered as ion exchange where you have a silica beads inside the column. Yeah, and you can also combine adsorption and ion exchange. Yeah, so under adsorption we have normal and reverse. So we look at what are the characteristics of normal and reverse. For adsorption, reverse phased, okay. Analytes usually with low to high polarity. Separation is based on polarity, okay. Non-polar sample matrix. Least polar compound elute first, so that will be normal. If it is reverse, okay, the analytes with moderate to low polarity separate based on hydrophobicity. So hydrophobicity, I hope that you know what is hydrophobicity. It is based on uh, how much it dissolves in water. And it is for aqueous sample matrix. Most polar compound will be eluted first. So we have to know the characteristic of this adsorbent that you have. Okay, adsorbent that you have. And then types of analytes that of your interest, whether you have moderate to low polarity or low to high polarity. Okay. And what types of sample? In this case, you have non-polar. For normal, you have non-polar sample matrix. For reverse, you have aqueous sample matrix. Okay. So the types of solid phase adsorbent that you can use for example, for reverse, for normal, for cation, for ion exchange, you can look at the examples in, I think I have given you this site, uh, LibreText, I think, where you can refer more on solid phase extraction. I think I have given you on Monday. Yeah. Right. So you have to know which is suitable for your application. So let's look at this. This is a Kool-Aid is a drink, and it is colorful drink. So in this case, IPA is isopropanol. Yeah, isopropyl alcohol. Uh, and this isopropyl alcohol is very popular for disinfection, okay, because it is what the water solubility of isopropyl alcohol is actually very good. So that's why for this reverse phase, if we look at what is the reverse phase, is analyzed with moderate to low polarity. So it starts with separating the moderate polar and until the lowest polar. So hydrophobicity. So lowest polar will be hydrophobic, and then it is based on aqueous sample matrix. So most polar compound will be eluted first, right? So if you look at here, the first is water. Of course, water is the most polar in this case. If we just use flush with water, so all the water will be out from the Kool-Aid, okay? And the second one, start using 8% isopropyl. So you can see separation of colors. So we can see that the red one is the most polar, and then followed by the blue one, and in the end we get the non-polar analytes. Okay, so this is an example of how separation in solid phase extraction by using reverse phase. Now, if we look at normal phase SPE, so we look at what is normal phase can be used. So analytes with low to high polarity and until neutral. So it's actually opposite of reverse. It start with low to high. This one start from moderate to low. Separate based on polarity. And the actual sample, the starting sample is non-polar. Yeah, it's not aqueous. So least polar compounds will be eluted first, whereas for reverse, the most polar will be eluted first. So we look at this structure. This is polyaromatic hydrocarbon, PAH. Commonly, we want to remove this PAH from water. So normal phase SPE are commonly used when the analyte of interest has low to high polarity or neutral. The cartridge contains polar absorbance, okay, because the separation is based on polarity. For example, silica. So this one is quite common. We use C18 if you are familiar with column chromatography. And this is an example of PAH in coffee. Yeah, okay. So this is the analysis of PAH in coffee samples. PAH, because of the aromatic hydrocarbon, they are yeah, reported to be carcinogenic, and it might be produced during the roasting process of the coffee beans. So in order to analyze, the coffee beans are ground up, dissolved, and the oily residue extracted into organic solvent. Okay, this extraction sample contain the PAH but also potential interference. So, so now in order for you to remove the interference, okay, so we are using SPE. So this one, if you look at here, dissolve and oily residue extracted. Sort of you have two extraction processes. Okay, so a bind and elute sample is used. Okay, so a PAH such as PAH is common. So there is you can see that the PAH, right, structure. They are aromatic. Yeah, they are aromatic. So there's a lot of pi electron. Okay, there's a lot of pi electron here. So how do the how do this PAH compound is trapped inside the absorbent is by the interaction of pi electrons interact with the polar functional group of silica. So you have to make sure about the structure. You have to make sure about the structure, whether you can, whether it will interact well with the adsorbent. So what happened is this is bind and elute, right? So now the PAH, so the blue analyte is supposed to be the PAH, the one that we want to trap inside the SPE, yeah, solid phase absorbent. And then we know that because of the pi electron, they interact with the functional group of silica, so they are trapped first. So the rest, that the interferent will be eluted out with proper solvent that can elute the rest of the interference. So once the interference is done, then we need to use a proper another solvent, a change of solvent to elute out the PAH that is trapped inside the that is bind with the SPE. Okay, the question is what kind of solvent? In order to elute the PAH from the cartridge, because the PAH, the pi electrons is interacting with the polar functional groups. So what kind of solvent do you think can detach them? What kind of solvent you can use to detach the PAH from the silica? So you have to know the right polarity of the solvent, whether you need to use more polar or less polar to detach the PAH from the SPE. If we wanted to use SPE in the preparation of soda and tea samples, okay, which type of absorption would we use, normal or reverse phase? So I think you can guess, because whether you have aqueous samples, whether you have what kind of compounds that you wish to take out from the samples, or what kind of interference that you want to remove. So you have to match them with the suitable technique. Okay. The next one, which be the last one, is the ion exchange. Yeah, ion exchange. Usually this is a bit difficult because the resin has to be requires to have a special ions on top of the solid phase extraction, solid phase adsorbent. So you need to have a cation or anion on the surface of the adsorbent, sorry. So ion exchange, SPE, lets a separate compound based on charge. Okay, so this is more suitable with charge. So let's look at the table just now, okay? So if it is ion exchange based on cationic adsorbent, the analytes are positive in charge. Okay, so again, it's a separate based on charge, and usually aqueous sample matrix with low ionic strength. So you have to know what is ionic strength. Okay, weakly ionized compound, of course, the one that is weakly ionized will be eluted first, because it is not attracted to the functional group on the cationic functional group on the adsorbent. So if it is anion based ion exchange, then the analytes are negative in charge, the rest are similar. Okay, so you have to know what is the charges of the analytes that you wish to separate to match with the what types of ion exchange that you wish to use. Yeah. So starting with the first step again, so I think it's quite similar. So similar steps, you wash, and then you start with the first components, what you want to separate, and it's up to the procedures, the next procedures. So let's say we look at this issue. The compound is I don't know how to put punicalagin is present in pomegranate juice. So punicalagin analysis in pomegranate juice can be a method of quantifying how much pomegranate juice is in juice blend. So this is probably the main content in pomegranate juice. Note that this punicalagin is colorless, and it is anthocyanin compounds that give pomegranate juices their red color. It's colorless and it is right, okay, understood. So anthocyanin compounds that give from. Consider the various SPE modes that we have discussed. We have normal, reverse. Oh, sorry. We have normal. Why do you want? We have normal, reversed, and ion exchange. So consider the most appropriate methods to extract punicalagin from pomegranate juice. Suggest both absorbent material and the eluents, means the solvents. Okay, what would be the first step that you do? Okay, I'm trying to adjust my. What would be the first step? Yes? Any suggestion? Okay, if you are to design the extraction procedure, what would be the first step to do? Any idea, please?
Determine the analyte polar.
Sorry?
Determine the analyte polar or the polarity of the analyte.
Yes, it is correct. But how do you in the beginning, because sometimes you don't have the information. Yeah, you don't have, because not all information of the polarity is listed. But looking at the structure, what do you look at the structure? Anyone apart from Hidayah? Can we have some more? That's why I put the structure. Okay, any comment?
Hydrogen bond,
Yes.
hydrogen bonding, the based on their group,
What functional group do you observe?
hydroxyl.
Hydroxyl. There's a lot of hydroxyl, right?
Yes,
What do you suspect? Is it a polar compound, or less polar, or probably non-polar?
polar.
It's a polar compound, right? So you start with that. All right. So next person. So you now have polar compound, right? And then we have again the three uh, types of SPE just now: normal, reverse, ion exchange, right? So next one, I don't know who answered just now. So next person, which one do you suggest? Reverse. Normal, reverse, ion exchange. Hello.
Normal.
If it is normal, okay, let's look at, I don't know whether, probably you're right. Okay. If it is normal, okay. If it is normal, the analytes with low to high polarity, okay, it might fit what we predict. Separate based on polarity, again, it fits the, the structure, but it is non-polar sample matrix. What do you mean? What do you know about non-polar sample matrix? If you look at the problem, okay, we are analyzing pomegranate juice, right? So is it polar or non-polar?
From structure is polar.
Structure is polar, yes. We want to identify now whether we are supposed to use, well, the best I think is normal or reverse, right? Normal or
Yes.
reverse. Okay. But now, when we read just now, that for normal, it is based on non-polar matrix, right?
Yes.
So is pomegranate juice a non-polar or polar matrix? Matrix means the sample. Is it?
Polarimetry.
Yeah. So which one do you think?
Reverse.
Yeah, because yeah, we can at least decide that the pomegranate juice is based on water, because we don't drink organic solvent, right? Okay, we drink water. So if we look at it, the factor, it is aqueous sample matrix. Means that the pomegranate juice is prepared in water. So it is aqueous. So I think the best option now is we stick to reversed. Okay. And we have to find a suitable um, solvent. Okay. All right, because each type of adsorbent are different, so they are designed for different purpose based on different metrics. Yeah. So if you start with just now, we have another example just now is PAH, right? But PAH, it is, you can see the preparation of analysis of the PAH from coffee beans. It is prepared in organic solvent, 1-betaine. Okay, so definitely the one that suits here is the normal, yeah, because the starting sample here is organic, yeah, organic solvent. But in the analysis of this pomegranate juice, because the starting sample is aqueous, so we have to use the reverse, yeah. So it's good. The first thing that we look at is the chemical structure, and we somehow can predict it is polar. Okay, so we look at the material, sorry, the matrix sample, whether it's non-polar or it is in polar in polar uh, mixture. Okay, so we know that it's a juice, so people drink water-based juice. We don't prepare in organic. So the possible way to do the analysis is by using the the reverse SPE. But of course, this is just a bit, you know, a very general one. So the question is, you have to suggest the exact, not the exact, the possible adsorbent material, means that what are the material. So please refer to the notes that the link that I have given, LibreText, I think in PDF as well. Okay, so there's a table suggesting what kind of adsorbent material suitable for certain things. I think I have given, so please look at it. But the most important is types of eluents, means solvent to extract the punis punicalagin from the pomegranate juice. Okay, right. Okay, because I don't have anything more. Right. There's a lot of setup for solid phase. This different kind of solid phase extraction. So the simplest one is in the picture. It is called it looks like a syringe, but it's a cartridge where you can put the absorbent inside. Yeah. You can use column chromatography, but as long as you use proper adsorbent, yeah, for the separation. Well, I forgot actually to, yeah, so the record, okay, the recording is on. I forgot. So, any question or any suggestion? Not much, because I'm not discussing the mathematical equation with you. If it is with the mathematical equation, it's going to take some time. It's playing with formulas. So I think you have passed that during your undergraduate. So I don't think it is important right now. The important is for you to suggest the strategy which is the best. Okay, all right.